Hey there, this is Mrs. Chabot. This is for my Calculus 3 class. So this is number 13 from the 15.7 practice problems. So you're asked to find the absolute maximum and absolute minimum of f of xy over a closed region, and the closed region is given to us in terms of the vertices of the region. So is the region bounded between these three vertices, um, 0, 0, and 0, 3, and 1, 3. Okay, and of course MyMathLab changes the numbers, so you probably have some other vertices still forming a triangle. Okay, so the region would be everything in this region here. Okay, so that's the domain of our function. We know that there is an absolute maximum and an absolute minimum because f of xy is continuous, and we're looking at it over a closed bounded region. Okay, so the absolute maximum and absolute minimum could occur at a critical point of the function, somewhere on the interior, or it could occur on the boundary. So let's start by looking for critical points. First, I need the partial derivative with respect to x. So f sub x would be 4x minus 4. And if I set that equal to 0, I get x equals 1. And then the partial with respect to y, f sub y would be 2y minus 6. I'll set that equal to 0, and I would get y equals 3. So there's one critical point, which is 1, 3. And here that actually is not in the interior, but it is in that region. So if it were in the interior, I would definitely look at it now. I'd be looking at these edges later anyway, but just as a general strategy, I would go ahead and evaluate the function at any critical points of the region. Okay, so f of 1, 3 would be 2 times 1 minus 4 times 1 plus 3 squared is 9 minus 6 times 3 is 18 plus 1, and I would simplify that to get negative 20 plus 10 is negative 10. Okay, so I would make a note of that. Like I said, especially if that were in the interior, the function value at that critical point is negative 10. So that's one possibility for absolute extreme values. Okay, now I need to look at the boundary. Okay, but unlike for number 12, I need to actually consider each of these three line segments separately. All right, so I'll start with this line segment on the y-axis. So that's where x equals 0. So I will call this function g sub 1 of, so I'll be in terms of y, because I can replace x with 0. So look at your f of xy, but on this line segment, x is always 0. So we would have 0 minus 0 plus y squared minus 6y plus 1. Okay. Now I'm going to look for essentially critical points on that boundary. So we would take the derivative, and we get 2y minus 6, right? So I'm looking at critical points of this one variable function. All right, so if I set that equal to 0, this looks familiar, I would get y equals 3. Okay, but it's on this boundary, so x equals 0, y equals 3, which would be of more interest if it were somewhere in the middle of the line segment, because I'd be looking at those corners anyway, but I'll go ahead and find it. Okay, so on this line segment, the only possibility for an extreme value is at this point 0, 3. So I'd plug that into f. So I get, well, we already know we have 0 minus 0, so we're just plugging in 3 for y. We get 9 minus 18 plus 1. which gives us -8. Okay, so let me label that. Okay, so there's another possibility for extreme values. At that point, the function has the value -8. Okay. All right, so that was that line segment. All right, so let's do this line segment. So that's where y equals 3. Okay, so we'll set y equal to 3, and we'll look at, again, a function of one variable. So it's this function specifically when y equals 3. So this is going to be a function of x, but I'll call it g sub 2 of x. So it'd be 2x squared minus 4x, and then I can replace all the y values with 3. So it'd be plus 9 minus 18 plus 1. Okay. All right, so looking at the derivative of that, right, so the only possibilities for an extreme value, a maximum or minimum, would be at the critical values on this line segment, okay, or the endpoints. Okay, so my derivative is 4x minus 4, and if I set that equal to 0, I get x equals 1. So remember, y equals 3, x equals 1. So I'm looking at f of 1, 3. Okay, and so again, that happened at an endpoint, so it's a little less interesting, but I'm looking for any critical values on this line segment. Okay, so I'd look at f of 1, 3. Okay, so plugging in 1 for x, I get 2 minus 4. I already plugged in 3 for y, which simplified to -8. So that all simplifies to -10. And of course it does, because I found that a few minutes ago. I did not need to find that again. All right, so we get -10. And finally, let's look at this last line segment. So let's write an equation for this line. So it'd be y equals, the slope, notice, is 3, right? Up 3 over to the right 1. So the slope is 3x. And the y-intercept is 0. So it would just be y equals 3x. All right, so I will write a new function, g sub 3 of, we'll write it as a function of x, because I can replace all the y's with 3x. So looking at our f of xy, replacing y with 3x, I get 2x squared minus 4x plus 3x squared minus 6 times 3x plus 1. So I get this g sub 3 equals 2x squared minus 4x plus 9x squared minus 18x plus 1. Okay, simplifying, we get g sub 3 of x equals 11x squared minus 22x plus 1. Again, we're looking for critical values along that boundary line. So we're going to take the derivative. So g prime of x equals 22x minus 22. Setting that equal to 0, I get x equals 1. Okay, so the point of interest we found here, y equals 1, and remember, sorry, x equals 1, and y equals 3x. So that would give us y equals 3, right? We're getting that same point of interest that we already evaluated. We know the function value there is -10. Okay, so I've looked for critical points on the interior. I've looked for critical values along those boundary lines. And the very last thing to consider is any endpoints. So we've already evaluated at these two endpoints. So all that's left is to consider this last endpoint, 0, 0. Whoops, endpoints. So f of 0, 0, we can see equals 1. Okay, so I'm going to go back up to my function, or my little sketch here. And at 0, 0, the function value is 1. Okay, so those are all the possibilities for extreme values. And now we know the biggest is going to be the absolute maximum, and the smallest would be the absolute minimum. So I have the absolute maximum is 1, and we see it's located at the point 0, 0 in the domain. And the absolute minimum is -10, which is located at 1, 3 in the domain. All right, and that's all there is to it. The worksheet this week, has some more points of interest along the interior and the boundaries, but this is the general strategy, and hopefully you found it helpful. Have a good one.